Hi, this is the second of my talks. This is on two approaches to health and safety within CRA. That's Consing Rio Tinto of Australia. Company was reorganised. This goes back to 1991, which is when I started working for them. At the time I was manager of cast products at the Camalco Research and Technology Centre in Melbourne. And then I went on to the principal consultant on safety within Camalco Research and Technology. I'm now Director of Strategic Safety Systems Limited in Cheltenham. The approach to health and safety in Australia, just to clear things up for those in the UK, is it's exactly the same as the UK, as it is post the Rogan's report in 1975 at the time. So we've got a Health and Safety at Work Act in Australia. It's structured differently to the one in the UK, but it's essentially the same. It is state-based, by the way. So there's one done for there's a Health and Safety at Work Act for Victoria. There's a slightly different one for the one in Queensland. I think, so for example, Victoria says there's a duty of care. In Queensland it says there's an obligation. But the same things are the same. You've got supporting regulations, much in the same way as we've got the cost regulations and the management of health and safety regulations. And there's a requirement for risk assessments, etc. So all of that. So it's very much the same as the UK. If we're just looking at the sites that we've got here, I'll mention this one here. This is Camalco Minerals and Alumina. I should stress that I was working for Camalco, which was one of the companies within CRA. I'll talk about that in a bit more detail there. And that's Camalco's Minerals and Alumina. They're at Weipa, and it's a site where bauxite is mined. There's another one down here, which is Boyne Smelters Limited, BSL. It's a site which is managed by Camalco. I think Camalco got a 50% interest or had a 50% interest in Boyne Smelters at the time. It's an aluminium smelter, so we're taking essentially alumina, which originates at Weipa, and turn it into aluminium there. We've got a site down here, Camalco Rolled Products in Yennora, a suburb of Sydney. They take solid aluminium, either as purity metal or as scrap, remelt it, cast it into blocks, about 8-ton blocks, and those blocks are then rolled down into sheet material. There's two sites that do that. There's one at Yennora here in Sydney, and there's another one, which is this one, which is Commonwealth Aluminum, and that's at Lewisport, Kentucky, quite a long way away. We've got the site that I worked at here, Camalco Research and Technology in Thomastown. I had a load of casting operations, so we could cast up to 5 tons. These guys down here were casting, something like 45 tons at a time. We could cast 5 tons. Camalco Smelting down here. It's a smelter. It's wholly owned by Camalco. And then finally we've got this smelter down here, a New Zealand aluminium smelters, NZAS, at T.Y. Point near Invercargill. Similar to BSL in that it's we've got Camalco had a 50% share in it, but Camalco managed it entirely, managed through Camalco Smelting. To give you some idea of what the sites were like, this is BSL, Boyne Smelters, on the coast in Queensland. Essentially it comprises, this is a support plant, a carbon plant. I'll tell you a bit about that in a minute. But we've got 2 long lines of reduction cells. One in here and another one in here. This bit is where a third line was put up. And to give you some idea of the size of this plant, this is gigantic. That's a 2-storey office block. And these buildings here were nearly a kilometre long. So they were massive buildings, big plants. Here's a picture of NZAS, New Zealand Aluminium Smelters, at T.Y. Point down in right on the southern tip of New Zealand. The reason it's there is because of electricity, and you'll see why that's important. If we look at that in more detail, then you'll see there's, again, long sheds like this. 6 of them, 6 bays here. And you'll see why they are long bays like that. There's a 7th one which was added here later on, and I was involved in that. This is the kind of structure of personnel within CRA, what's referred to as strata. Lots of people at stratum 1, so everybody was at stratum 1, everybody on the shop floor, etc. If you were to get a supervisor, a project leader, they would be at stratum 2. If you were like me and you were a manager, I was managing about 30 people at the time, then you will be at stratum 3. So you could be a manager or a principal consultant at stratum 3. So here we're showing managers. I'm a manager of metal products and manager of carbon. You had another manager of reduction, etc. We go up to a site level. We've got the general manager who's at stratum 4, so we have a general manager for New Zealand aluminium smelters, another one for Boyne smelters, another one for Velbay, etc. He was at stratum 4. You also had chief consultants at stratum 4 as well. Same level of complexity, the work of somebody who might have a plant with several hundred people there. At stratum 5, you had managing directors or vice presidents. So you had a managing director of Camalco Smelting, a guy called Carl Stewart at the time. You had a vice president of Camalco Research and Technology, a guy called Tony Kerr. I'll talk about him in more detail in a minute. At stratum 6, you had the group executive, one person there for Camalco. You had another group executive for Hammersley Iron, another company within the CRA group. And right at the top, you had stratum 7, which is the chief executive, just one person there. Right, I'm going to talk about aluminium. Camalco, the word Camalco comes from Commonwealth Aluminium Company. So we're talking about aluminium because that's where the dangers were that I was involved in. We start with this stuff, alumina, aluminium oxide, and you pump in a lot of energy to break the bond. And you end up with aluminium and oxygen. Right, I say lots of energy. Well, how's that done? Well, essentially, we've got these kind of tubs here. You've got a case in there. It's got a carbon liner on it, and inside there we have a substance called cryolite, aluminium sodium fluoride, and that's at about 900 degrees C. And you dissolve alumina in there, your aluminium oxide, that goes into there. And coming into it, we've got these things which are anodes. And we pass an electrical current between the anode and the cathode, because that's liner there, that carbon liner is the cathode. The anodes get eroded away, so they get burnt away. So you'll see this one has kind of gone down a bit, and this one's a new one. And to keep this distance, the correct distance, this whole thing moves up and down. And so this cable bringing the electrical current in is flexible. And you daisy chain them together, like that. So the reason for having long sheds is that these are all in one line. You'll probably have something like 200 of them in a line. At BSL, Boyne Smelters Limited, they're in one long line. At New Zealand aluminium smelters, it's a U shape. So you have 100 going up on one bay. The buzz bars here go across to the next bay, and it comes back again another 100. So we had about 600 of these at New Zealand aluminium smelters, and at the time about 400 and then a similar number at Camalco Smelting. Right. This is what it looks like in practice. This is a Camalco CD200 reduction cell. And these are new ones that went into New Zealand aluminium smelters. They're not the ones that were majority in use. That came in later. And you'll see this is the thing that goes up and down a bit in there, inside there. This is one of the cables bringing in the current. This is flexible. There are 3 of them. So you may guess from that, the size of that, you can get a feeling for just how big this thing is. But these say that these are handles that you grab hold of to take those covers off. You may get a feeling for how much energy is involved by just looking at the size of that, and that's only a third of it. And the actual energy you've got is that you've got, this one is rated, the 200 CD200 means that it can actually run at 200,000 amps. So there's 200,000 amps going through between the anodes and the cathodes. Volt drop of about 4.2 volts. In fairness, at New Zealand, they didn't have 200,000 amps. They actually ran at 167,000 amps. But each one of those is about 750 kilowatts if you do the sums, multiply those up. So you're pumping in this vast amount of energy to produce aluminium and oxygen. The only snag is that it can go back the other way. So aluminium can combine with oxygen to produce an oxide and release that energy that you pumped into it. It does this at any temperature, by the way. It will do this at room temperature. The good news is that it only does it at the surface layer. So you won't get, your aluminium in your aeroplane is not going to turn back into a white powder. It will only do it at the surface. So you just got to be worried about those situations where you can get a new surface, because as soon as you expose a new surface, then you'll get this thing happening instantly, effective as far as you and I are concerned, instantly, and you'll get lots of energy given off. The energy release sequence, if we take something like molten aluminium, because molten, so it can do it at any temperature. It doesn't have to be hot to cause this, but it has to be hot to be molten. And if you've got some kind of trigger which disturbs the molten aluminium, then you get this kind of sequence. The worst thing you can have is some kind of ejection. So something which causes molten aluminium to be thrown up into the air will produce a spray of molten aluminium, a lot of surface area, instant generation of the oxide. So we get thrown up into the air, we get a new surface created. That new surface creation causes oxide to be formed. That oxide form means that you're going to get energy released, and your nightmare scenario is if some of that energy at least goes round to eject more material, and then you get a runaway sequence. You may call it a chain reaction. You get a runaway sequence, and you've got a major explosion. When I say major explosion, what are we talking about? Well, this happened in 1979. As I mentioned before, Comalco Rolled Products melted scrap material, and other purity material, and some of it had water running off it. Hadn't been properly dried. So it was about to be tipped by the crane operator into the furnace. Now the furnace design, as it stood at the time, was it was a round tub basically with a lid which was moved off the charging, and you dump the stuff in from the top. This guy was about to dump all this stuff in, and his workmates said, "Don't do that, mate, that's bloody dangerous." And he said, "No, it's all right." They legged it when he continued to do this. And the result was this. The crane driver was sitting in his cab there. This is the furnace with the lid off it. And that's the level of destruction we've got within that plant. He was killed, obviously. Unfortunately, not instantly. This is the another view of the plant. You can see how much destruction there is here. I don't have the picture, but I wish I did. But there is a picture that was taken inside this building there, and it's under this hole there, and that is caused by a bit of block. Now, when I talk about block, I mean this. This is the kind of product that's produced. That's a rolling block. It's about 8 meters long. This is about 1.5 meters across there. And I won't go into the details, but basically you saw off these ends here because these are scrap, top and bottom. We're not into steady state casting conditions, so metallurgically it's not right. So you saw those off and you remelt them. So you can imagine something like that, a block like that, had been thrown out of the furnace, out of the building, and had crashed back through the roof, and that was what was shown in that picture there. That's the kind of product we're talking about, rolling block. You'd cast, they're cast vertically, by the way. I'll tell you about that in a minute. Here's some other products that we're talking about. These are billets. They're cast vertically in this kind of matrix that is shown there. This, which is ingot, which goes to be remelted. Said that it's cast vertically. The way it's done is through what's called vertical direct chill casting. So you've got a furnace which you can tip up here, and that goes into this trough here, this launder, and it goes out to the mould. And mould is just this circular thing here, and it's got a base to it. And the base is supported on a hydraulic ram. You're pouring water onto this, so metal goes in and it starts to solidify, and as it does that, the ram descends and the product grows like that. You'll get a water being sprayed directly onto the product itself, which is why it's called direct chill, and the thing will grow downwards like that. And you'd have as a product something like an 8 by 8 matrix of 172 billet, 172 millimeter diameter billet. 172 seems a bit strange, it's 7 inches. Strange situation there. That'd be about 7 meters long. Or rolling block around about 5 meters long or so. The pit would be typically 8 meters here, and we've got water in the bottom of it. Now, water and aluminium, molten aluminium, are not good bedfellows. If you put water onto molten aluminium, then it's not a good idea to do it, but it will just sizzle and disappear. If you get water under molten aluminium, then it will expand dramatically as it turns to steam, and that expansion will cause the aluminium to be thrown out, and that's one of your nightmare scenarios. Lots of things you can get out here. As I said, you can get steam explosion with materials there, with these out onto water or whatever. You can get a chemical reaction with oxides, because we'll react with oxygen in any way. And there's another one which is a peculiar one here, which is lightning, which happened at one site. Let's look at the types of aluminium explosions that we had. The one I've just mentioned before was at Unora, our plant there, where the crane driver was killed, and that was caused by water. There was another one in 1986 where 4 people were killed at Sims Metal in Melbourne. That was caused by nitrates. They were using sodium chloride as a flux, and that was being added to molten aluminium. But they also apparently use sodium nitrate within that plant, in the same kind of bags, in 25 kilogram bags, and just so happened that somebody made a mistake and added bags of sodium nitrate to a furnace of aluminium, and up it went and killed 4 people. The last one was at a smelter operated by Péchenay at Issoire in France, and that was caused by a lightning strike. We don't know the full details of exactly what happened, but we think it kind of arced across from a drain pipe, and that caused something worse than aluminium being thrown up into the air. It virtually evaporated, and that caused a major explosion. Right. The molten metal safety approach, and we decided, or the Board of Comalco decided in 1991 that they were going to re-look at molten metal in a serious way. And they did the following thing. They appointed a board member. So there was a board member who was made accountable. That was a guy called Tony Kerr, who was my vice president of Comalco Research and Technology. He then nominated molten metal steering group members. Now, this is the original 1991 molten metal steering group. Obviously, you have Tony Kerr, who was the head of this, but then the key thing was that you had the key people from each site. So these were the metal products managers. These were the people that were working with molten aluminium when it was being cast, when it was coming near water, for example. We had Dave Rao from Comalco Smelting. We had Scott Thomas from from Commonwealth Aluminum in Kentucky. Russell Luxford from Boyne Smelters. I had me from Comalco Research and Technology, but I was supported initially by one of my guys, Alan Clark, because I started working on this 4 days after I joined Comalco. So I'd moved my family across to the other side of the world, and 4 days later I was working on molten and aluminium safety. We had Bob Hartley from New Zealand Aluminium Smelters, Dave Solomon from Comalco Rock Products. Now these other three were external people. We used the services of Lindsay Mallon from ICI Australia. So he was a safety expert. So we've got a safety expert. We've got the people who know the process. And this person is a key safety expert. We had Alex Bull, who was retired, but he used to work for Comalco Research and Comalco Roll Products. And we also had Elwyn Roy, who was again retired, but he was one of the key people on molten aluminium safety within the Aluminium Company of America. So we've got the molten metal steering group members. I should stress that one of the problems with CRA was they did move people around a lot. As I said, I had 2 roles. That was not unusual. Most people in a Stratum 3 manager level would expect to move every 3 years. One thing we did was to then define benchmark standards, because you can't go and get an ACOP off the shelf. There was something done by the Aluminum Association, but we had to define our standards. And that was done originally by Alan Clark. Alex Ball added to it considerably over the next couple of years, and then I kind of reworked it in 1995 to actually make it a bit more palatable, because it was getting a bit unworkable at that time. We then audited against those standards. So we had key people from the molten metal steering group actually audited those sites. So you were being audited by your peers. This was a peer review. They, at the point at the end of the audit, they would provide a report, not a fully written report, but they would do a presentation. In those days, it was acetate slides for overhead projectors, written in hotel rooms at night. Now, the important thing was that it was done as 2 presentations. The first one was to the workforce. This was incredibly powerful. You actually went and told the people who were at risk what the risks were and what the problems were before anybody else got to hear. the general manager got to hear about it later, but it was initially to the workforce with their managers present. The key thing was that this guy was present, ARK, that's Tony Kerr, the person who is responsible at the top for this. So he was there at every presentation. He was there. He was seen to be committed to this. Everybody knew his face, everybody knew who he was. There was commitment right from the top, and it was visible commitment. We then had a second presentation to the general manager of operations at the site, so he was told about it after his workforce had heard about it. And then a copy went to the business unit managing director, with a copy to the board. So if it was a Camarco smelting site, it would have gone to Carl Stewart, who was the managing director of Camarco Smelting. There was an action plan that came out of it, but the audit team didn't specify what the action should be. They could offer, could make recommendations, but it was down to the site to decide what to do and specify the action plan. There was an initial round of compliance audits in 1991. I wasn't. The first one was at Bell Bay, Camarco Smelting in Bell Bay in Tasmania. I wasn't part of that. I went to the one later on in 1991 at New Zealand Aluminium Smelter. Other ones at all over the site. But there were things that really needed to be done. There were some major problems here. As people change roles, I mentioned that CRA forever changing their people, particularly people in manager roles and senior manager role and in managing directors were moved quite often. But we always had a metal product manager or cast house manager from each site as part of the molten metal steering team, as part of the audit team. We did another round of audits in those 2 years here, and we used other people as well. So we had people in Stratum 2 levels, supervisor levels, but we also had people in Stratum 4 levels, chief consultants. So we mixed a whole load of people, but it was still peer review. It was still done within the company, and then we stretched it to cover other things apart from molten metal. After a while, originally it was funded through Camarco Research and Technology, but after that it was financed out of your own budget. So to be part of the molten metal steering group, it came out of your departmental budget. But there was always a clamour to be on this team. We revised the benchmark standards and we carried out some more audits. The strength really was that it was targeted to real and serious hazard. Get this wrong, then there's an explosion. And with an explosion, people get killed. So this was a real and serious hazard, and everybody accepted that. It had the full enthusiastic, and I can't stress this enough, it was the visible support of a board member. And as Tony Kerr moved on to other roles within CRA, but his successors did exactly the same thing. It wasn't just him, it was inherent in the whole thing. It was by peer groups. It wasn't some bloke coming in from outside. It was by people that were working in exactly the same conditions as you in other sites. And as a result, we got good transfer of practices. You'd get good practices. Somebody would look at that and say, that's a good idea. I'm going to take that back and apply it at my own site. And an awareness of bad practices. They'd look at it and say, ooh, gosh, that's a bit dodgy. I wonder what we're like. We'd better check up on that. And as I said, there was generally a clamour to be on the team. It was actually seen as a career-enhancing move, particularly within Camarco Smelting, because of the enthusiasm of just how well it was working and the enthusiasm of the managing director. So it was a really good situation. Now I'm going to compare it with this, which is the NOSA system. It's a South African system, National Occupational Safety Assessment System, Association system. It was introduced within Hammersley Iron. That's one of the other groups within CRA. It was introduced around about 1991 that we started to introduce the molten metal thing within Comalco. It was introduced across all of CRA shortly after that. And what you had was a little green book. I do apologise for the quality of this. But basically, there was a book, and it had lots of questions that could be asked. Looked at things that you go into, and you see these numbers here, and these are scores. So you'd actually get a score against it. And if we looked at the whole list of stuff, you'd find that you get this scoring thing down here. So, for example, machine and hazard guard, you could get 100 for it. Incident and hazard report, again 80. Now this is strange. This one here, personal protective equipment, 65. Now, most in-line people would actually put personal protective equipment as the last-ditch method. But here we're actually saying it's so important we give it a very high score. Now, if you're a manager and you're being held accountable for getting a good score, and that's what was actually happening, then what are you going to do? You're going to put all the effort, what gives you the biggest scores. So this is where you put the effort in, and you ignore some of the stuff down here. So, for example, or work permits, permit to work. Well, that's very limited. The other thing which you might notice here is there's some whopping great gaps. There's nothing about risk assessment. Risk assessment is a requirement, a legal requirement of the Australian system, same as in the UK. It's not a requirement of the South African system, which this came from. So risk assessment wasn't there. Nothing about manual handling. Manual handling accounts for about 40% of the injuries that we get. However, no, it's not covered in this. There's nothing about confined spaces. So there's some whopping great gaps in here. So the problems that we get is that it's tailored towards a typical company. We ignore these major risks if they weren't part of the system. It didn't address the legal requirements. So as I mentioned, there was a requirement within Australia to carry out risk assessments. Well, it's not in there, so we ignore it. It did introduce spurious requirements. I could give you some examples, but I won't. But it diverted attention away from the real problems. So if you weren't considering, molten metal safety wasn't considered. Neither was confined spaces or manual handling. So we ignored that. And there was no transfer of practices between sites. The molten metal steering or management system was good because people were learning from different sites and carrying out, and you actually found out good things and bad things about other sites. Because it was resented by, because it didn't tackle the main things, it was resented by most people. I always remember one of my colleagues who was managed health and safety at the smelter at Bell Bay actually told the auditor when he came in, said, right, we've had 3 instances since the site was commissioned, which was in 1955. We've had 3 instances where a person has had a foot amputated. Basically, they've gone through the crust and put their foot into cryoline. And the auditor was not the least bit concerned about that. He was saying, well, let's have a look at your lighting survey. And no suspected had no respect whatsoever. And then finally, it was incredibly, ignored good practices and performance, which is because it was transferred between cycles. Finally, it didn't have much of an impact on safety performance. I was lucky because when I was asked to implement the NOSA system at my site in Melbourne, I told my vice president at the time that the NOSA system had lots of holes in it. It's some real major problems. And he said, don't worry about the NOSA system and the score you're going to get. Do the things which are right. If you get a poor score, that's my political battle. I'll cope with that. You get things right. So I was allowed to do things which were outside the NOSA system and get on with other things as well. Let's have a look at how well it worked. Well, it made an improvement. So across the whole CRA group, it went down. Lost time injury frequency rate went down. It went down from around about 21 to 18. It was an improvement there. If we look at the effort ratings, the best one in the whole group was Hammersley Iron at Dampier, port site there. They've got a 91% rating, so that was great. Best in CRA. Because I was allowed to do things which didn't give a good score, and to ignore some of the things which did give a good score but were meaningless, I got a lousy overall score. 54% we got. However, our lost time injury frequency rate just went down. Kind of went down and down and down, and if we were to plot it out for 96, we actually stopped injuring people. Right, so we did that from a lousy score. What happened at Hammersley Iron at Dampier, who got a wonderful score there? Well, you actually find that it got worse because they were putting all their effort into tackling things which gave them a good score rather than things which actually made things better. So the lessons that we've learned from this, and this is kind of really driven up my whole approach to health and safety management for the last 25 years. First of all, systems need to relate to the risks that are present, not some spurious checklist. You don't go in with this checklist and work to that. Systems need to be concise. You don't go in for a lot of waffle. You must know when to stop. If you pay pedantic attention to minor detail, then you lose focus, and the important things will get forgotten. Next thing is peer assessment is incredibly powerful. People are respected. If you're respected and audited by your peers, it's far better than somebody from outside. You may need to use external support from outside. I'm not going to turn down work, but you use this as a source of backup advice and not the policeman. Because if you only do the right thing when that person turns up on site, then it ain't going to work. Then ideally we use people from different sites or departments to inspect other sites or departments. So it's this peer assessment is where possible. Unfortunately, most companies don't do that. It's a shame because they really are missing out. I'll just leave you with this one, which I call the Chambers curve. If we plot safety here against effort, I don't know how you measure effort, it's time, certainly it's money, and there's this theoretical 100% safety, it's absolutely safe. So as you put more effort into something, then you'll get an improvement in safety. But as you start to do more, then that return drops off, and you'll get to some point where you're putting more and more effort and you aren't going to improve things. Now this is the contentious point, and most people would say that I should rot in hell for saying this, but I contend that if you keep on putting in the effort, then you will make things worse. So you know when to stop. Well, that is all my experience from managing health and safety within CRA and what I learnt from it over a 5-year period. I hope you've enjoyed this. Thanks. Bye.